Hello everyone. So it's a great pleasure to welcome Grant Kennedy today. Grant is coming from University of Warwick, where he's a lecturer. He has done his PhD in Australian National University, so he's coming from the South Hemisphere. And after this PhD, he has worked in Cambridge University, in particular with Wyatt. And he's involved in research in debris disk. He has done some work with a large binocular telescope, working with interferometry to look for exo-Zodiacal dust around stars. He has done also some direct images of exoplanets, but today we'll speak about a different subject. He will speak about the comets that orbit other stars, so also called the exocomets. Welcome, Grant, and we'll listen to you.
Thank you. And thank you for having me here. It's a pleasure to be here. And one of the reasons is this comets around other stars, the stuff that I'm going to talk about today. A lot of that work really started here with work by people like Alain. And so I'm going to tell you a little bit about some little bits that I've added to that. This is work that's been going on for over 30 years now. And so the work that I'm going to talk about are things that I've done, but it's also with a long list of collaborators. And so you'll see their names come up as we go. Right. So I want to start. So I'm going to talk about comets around other stars, but I want to start with a picture of a comet in the solar system, and this was one that came through the inner solar system in 2006 during my PhD in Australia. And this is a photo that was taken by Rob McNaught, and this comet was called Comet McNaught. And I think like our efforts to discover and characterize planets around other stars, I think our efforts to do the same thing for comets are inspired by what we see in the solar system. So I'm not going to be showing you any images of comets around other stars that look like this, of course. But this is sort of some of the inspiration. But of course, it's not just about inspiration for pretty pictures. We want to know what kind of science that we can do. And to give you just one example of the sort of thing that we try to do in the solar system by looking at our comets. This is an image of 67P from the Rosetta mission, and I just want to highlight one paper which is looked at the information from all of the instruments on board Rosetta and tried to come up with a picture of how this comet formed, and their conclusion is that it's an aggregate of objects that are all a few millimeters in size that have gently coalesced under gravity to form this object. And so in the solar system we can use comets to try and constrain how the planetesimals form, so these things that we call comets when they come close to the star, because these are also the things that we stick lots of them together to make planets. And so we want to ask questions from the comets to tell us about planet formation. And of course, this is also telling us about the planet formation that went on and where it went on. So these are some images plots that are made up of bodies that we know about in the solar system. So this is the inner solar system. So here is Earth and Jupiter. You see Jupiter, Trojans, and the asteroid belt and near objects that are nearer to Earth. And then we go out, zoom out. This is now Jupiter, and this is Pluto. And we have all of these objects out in what we call the Kuiper belt. And so this is where our comets come from. And so when we look at comets, we're really trying to probe the formation and the composition of these objects that are a long way away from the star. And so we do more than just look at what these bodies are made of. We look at other things. We want to know, for example, where did the Earth's water come from? And so we can look at the composition I'll look at D to H ratios, deuterium to hydrogen ratios in comets. And so these are some of the things that we do in the solar system with comets. Now, around other stars, of course, it's a lot harder. We don't get to send a Rosetta mission. Yes. So if you look, I think this direction here is towards the galactic plane or the galactic center, and so there are too many stars. So yes, this is incredibly biased. And so, for example, if you look up here, this will be from a very deep observation. So and this is so you may have heard of this debate about Planet 9. So do these objects tell you about another planet? And the problem is that these observations are very, very biased. And so if you look in one direction, you see lots of objects in one direction, and then you conclude that there's a planet that is putting these objects in one direction. And so some people just don't believe there's any evidence for Planet 9. So yes, this is more complete, but this is very biased. So as far as we know, it's smooth all the way around. Thank you. So to do this around other stars, we have a long list of questions that we would like to ask about comets around other stars. What do they correlate with? Do we see more around more massive or less massive stars? And what are they made of? So we want to ask the same kind of questions around other stars that we can ask in the solar system. But to do that, we need to find some comets first, and that's the hard part, and that's basically where we're at, and the sort of things that I'm going to talk about today. And so the kind of picture that we have is something that looks a little bit like this. So we have a star and we have a planetary system. So this here would be something that looks like our own Kuiper belt. So a bunch of small planetesimals. Maybe there's an asteroid belt, some planets like Earth, and some giant planets. And if we want to get these objects close to the star so that they are comets, then you need to have them interact with some planets, and they will make their way closer to the star where they can be observed. And so the standard solar system-like scenario, you have a disk out here of bodies, and then you have some planets, and they scatter off the planets and come into the star. But that's not a unique scenario. You could have, for example, an asteroid belt with some planets outside it as another way of getting objects close to the star. It doesn't need to be just like in the solar system. And so I'll just first talk a little bit about these things out here. So these things we call debris disks. And so these are analogues of the Kuiper belt in the solar system. And we take images of them. We've been taking images of them for 35 years. Now we take a lot of images of them with ALMA because it has very high sensitivity and good spatial resolution. And so this is one example image of something that looks very much like a ring. There are other objects, and so these objects, we really think that there's not a lot of gas. There are a bunch of planetesimals. They are colliding. They break down into dust, and then when we observe them, we observe the dust. Now there are other objects where there is circumstellar material, something like this. You may have seen this image of HL Tau. This is a gas-rich disk which is probably forming planets, and so this is not the sort of thing we're talking about. And there are other things. There are massive stars that are losing material in a planetary nebula or in a stellar wind. So these are not debris disks. But we also have some things which have more gas than we expect for a debris disk, but less gas than we expect for a young planet-forming disk. And these fall somewhere in between. And so it's not really obvious how to classify these things. And so when we look at these things, these are potential comet source regions around other stars. And we have lots of pictures of these now. Most of the The images in this gallery are from ALMA. I think it's almost, so there are a couple that are taken with scattered light. So this is imaging with sphere on the VLT. This is scattered light, but everything else has been imaged with ALMA. And ALMA has been really, really important for changing our view of these disks, both because we get this amazing resolution. So all of these things here are on a scale of 100 astronomical units, so similar, maybe a bit bigger than the solar system. And one of the things that I want to talk about, and it's good that Quintana's just come in because this is something that he works on as well, is that we can use ALMA to look at these debris disks in a way that was not possible before. And so we can look at them and think of them as comets or as objects that have ice in them that would be comets when they come closer to the star. And so there's a couple of things that I'll talk about. Now the first one is that we can detect CO in these disks. Now this had been done a little bit before, but the CO levels were sufficiently high. There was enough CO that we thought that maybe it was CO that was a remnant of it when it was a young disk. But now we have detections where the CO is very low, and it's also in the same place. So this is a continuum image, but we find CO in the same place as the dust, and we actually think that the CO is coming out of the dust. Now, even with ALMA, this is actually quite hard. There's no image. I'm not going to show you an image of the CO. This is in the 1.3 millimeter 2:1 transition. But what you have to do, so with ALMA you get a cube, so you have an image, and in each pixel there's a spectrum. And so what you can do is you can make a spectrum of all of the pixels that are in the same place as the dust is, and you get a spectrum like this. But as you go to different locations in the ring, because this is a rotating structure, the velocity is slightly different at each different location in the ring, meaning that your CO is spread out in velocity. And so what you can do is that you can correct for the velocities as shown in this plot. So these are the velocities in each pixel, and then you shift the spectrum in each pixel. And you have two choices. You can shift the spectra as if the disk is rotating this way or that way, and one of them is right and one of them is wrong. This one is right, this one is wrong. So if you shift all of the spectra in this cube in the correct way, then you get this peak from CO, and so this is a detection of CO in this disk around the nearby star Fomalhaut. And so we think because the CO is in the same place as the dust, that as you're breaking up the planetesimals, then CO is coming out, and we detect it in the spectrum. So now what you can do, and so this CO is very short-lived. It gets photodissociated just by photons that are in the interstellar radiation field. That's what this is. So this is one of the reasons that there is very low levels of CO, because it's short-lived. But what you can do is you can make an estimate. So if you know how long the CO is there for, and you can make an estimate of how much CO you might be producing with a factor FCO, you can make an estimate of how much CO there is in your comets. So you make an estimate where you figure out the fraction of CO in your comets is just the amount of CO that you've detected divided by the lifetime of the CO, and then you divide that by the amount of dust that you think you're producing. So you can estimate that by looking at the dust. And if you do that, then you can make this plot. And so what this is showing is the fraction of CO and CO2 in the comets for several systems around other stars, so Fomalhaut, HD 181327, and Beta Pic, and compare these with these CO fractions in comets in the solar system. And of course, this is hard, so we have large error bars, and in this case we have an upper limit, but as far as we can tell, the amount of CO in the comets or in these objects, the planetesimals in these belts around other stars have a similar composition to comets in the solar system. And so we've learned something. There's a lot more to do on this, but this is a good start. And one other thing that we've realised is that there is information in the sizes of these disks. So we take images of these disks and we measure their radii, and that gives you this axis. And then we figure out the luminosity of the star that they orbit, and then you put all of these disks that we have images of on this plot. And what we see is this correlation, and this correlation is not all due to this point. If we take this point away, you get the same correlation, where the size of the disk gets larger the more luminous star you have. And one of the reasons that we think that's interesting, it could be that there's a preferred temperature location in the disk where these belts are forming. And so that's because we have a few points here. So these are images of young disks with lots of gas in them that are probably forming planets. And this is roughly the distance at which the disk becomes cold enough that CO freezes out into ice. And so this may be telling us that, and this is where the Kuiper belt is in the solar system, this may be telling us that these disks tend to form where it becomes cold enough for there to be CO and ice. And so one of the things that we want to think about, is this telling us something about the composition of these objects as well? And there's a lot more work to do on this as well. This one here is a bit closer than the others, and it has no CO detected. It could be that this one was just a little bit too, in a location that was just a bit too hot. And so there was no CO ice in these planetesimals at that location. So this is just new work, so there's a lot more to do on this as well. Okay, so that's something about the source regions where we think these comets that we're going to look at around other stars come from. But we can also look at these objects when they get very close to their star, so close that they will go in front of the star. And you may have seen, I'm not sure if I've seen this image on the wall here. I've seen other images of the same disk. And so this was really the first evidence of a planetary system around another star. And so this was in the early to mid 1980s. And so this is this famous system called Beta Pictoris. And it has been studied a lot, partly by people here, a lot by people in France, but also a lot by people all over the world, because it's a nearby system. It's only 20 parsecs away, but it's very bright, so it makes it easier to study. And one of the things that we've discovered, is this a movie? Is that there is a planet, and this was a French discovery. This object called Beta Pic B, which is moving in the plane of the disk, and this is a series of images that Jason Wang has made into a movie. So we've known about this for over 10 years now, and so we're actually watching it move. And since this was made, it has now appeared on the other side of the star. And so this is the system that I'm going to talk about for several slides now. And so the original evidence for exocomets at all was work done here. So this is a high-resolution spectrum of one of the calcium H or K lines around Beta Pictoris. And so this is an A-type star. It's very rapidly rotating. And so the rapid rotation gives you this very broad absorption feature. And then there are two other things in this plot. So the other thing is that there's a stable absorption feature. So we think there's a disk of gas that is orbiting the star, and that gives you this absorption feature. And this is always there, and it doesn't really move. But if you look on different nights, and these are observations on different nights in the mid-1980s, you get these other absorption features, and they're basically different every night. And so the idea is that these were called falling evaporating bodies, and I think partly at the time, exocomet was not a word that you were allowed to use. People were very skeptical. You're not allowed to say of exocomet. But now, so this is one of Flavian Kiefer's papers, and instead of called FEBs, now it's okay to call them exocomets. And so we think that these are because they're different every night, you have an object, you look at it some night and there is one of these objects, a large ball of gas, at least in calcium, that is in front of the star. And it goes across in maybe a night or a few hours. But then you come back the next night and that one's gone and there's another one going in front of the star. And so this is why they look different every night. And we see them at different velocities as well. They tend to mostly be redshifted, so they're falling in towards the star. But some of them are blue shifted as well, so moving away from the star. And this has been ongoing for at least 35 years. So this is not something that's just happened for a few years. It seems to be going on at a similar level for at least as long as we've been observing beta Pic with high resolution spectra. And so one of the things that we think we've learned about this is if you take the last 15 years of spectra, so beta Pic has been observed with the HARP spectrograph in Chile thousands of times over the last 15 years. And so if you look at all of those absorption features and then start trying to group them, then one of the things that you find is it looks like they go into two groups. There are some that are at relatively high velocities and some that tend to be at reasonably low velocities. But if you look at other things that you can get from the spectra, and in particular the fraction of the star covered and the amount of absorption, it looks like you basically have two distinct families of comets. And so this is a little bit analogous to what we have in the solar system. We have different families of objects, which say give us the Perseid meteor shower. That's from a family of objects. And in particular, these ones that are at low velocity, we think those are further from the star, and those are relatively young comets. They have a lot more ices in them, and so they're a lot more active. But then these ones may, over time, evolve to be these ones, which are closer to the star. They're going faster, but they've been depleted in their volatiles. And so this is a hint of the possible evolution of these comets over time. Now, one of the things that was done fairly early after the discovery of these objects, it's by Hervé Buste, is to try and come up with a physical model rather than just fitting Gaussians to spectra. And the main conclusion from this, so you make a model where you have a comet and you have energy input from the star, and then that sublimates ices and you have material flowing off. And so the point of this was to model these objects as they are moving in front of the star. So in this plot here, there's a star here, there's a comet, and an observer over here, and you watch the comet go past, and at this point you can get an absorption feature in your spectrum, just like in the data that I was showing. And then if you change the distance from the star, this is in stellar radii, so this is very, very close to the star. And if you make it, so here 20, here 10, the difference is that the energy input from the star is greater because you're closer to the star, and it makes the coma of the comet smaller. So you expect that when you're further away from the star, you have a large coma around your comet, similar to the size of the star, but the closer you get, the smaller your coma gets. And then this has been used to derive the distance between the comet and the star, this model. So if you want to derive the distance of the comet to the star, you use this model. So it depends on your model, the answer that you get. Now, one of the things, this is where I started working on this. So I was looking in these data, and I realized that you can actually see the comets move and they change in velocity as they are moving across the front of the star. And so what this plot shows, so again, it's showing a whole bunch of spectra, so radial velocity, and in this plot, this is just a whole lot of spectra plotted on top of each other, and I've reversed the color scale. So this is 2 hours of observations, and what you see is the same circumstellar line here, and then there's another absorption line here that is stable, but then there's this weaker absorption line here which is moving, and you can see that as a line up here. And so this is the acceleration of the comet while it's still in front of the star. And this is really neat because gravity tells you what the acceleration of an object should be, and that depends on how far away the comet is from your star. And so this is a new piece of information that we can use. And so there are quite a few nights over the last decade or so where lots and lots of spectra have been taken. And so what I did is I went through all of those, and each of these plots are just like the last ones. And I've got little dotted lines which show you where there are absorption features that are moving. So they're not perfectly vertical, they're slightly tilted. And in all cases they're tilted this way, so the velocity is increasing, so they're falling into the star. They're accelerating towards the star, as you would expect. And so then what you can do is then you can, oh sorry. So there's a problem here in that if you want to, so this, maybe it's easy with this feature is always here. And so if you have something that's close to that, then it will be very hard to see. And so these ones are easier. So this is still moving, but they tend to be further away just because if you have strong absorption there, so it's kind of hard. It's hard to subtract that off. So all of this was basically a first go at this. I've not made an automated method this is very simple. Basically, I made these plots, and then I looked at them with my eye, and I picked out ones that were moving. And so this is not complete, and I'll show you that in a slide in a few minutes. That they do tend to be at velocities of more than 50 kilometers per second. And so then what I did is I fit these with basically a very simple absorption model, which has an orbit as well. So there's to fit it, but there's basically some kind of absorption, which was just a Gaussian. And then to figure out what the acceleration should be, then I take some orbital elements for that comet, and then I try and fit them. And the first thing that you can do with that is make a plot like this, which is showing the acceleration as a function of the velocity. So that's just the slope against where the absorption feature is. And so I fit them for lots of features, but the acceleration is not always constrained. So some of these, it's not. There are features in here, say like this one here, which if you try and fit it, it turns out to be consistent with zero velocity. And so what I did is I fit this with a Markov chain Monte Carlo method. So basically, you get a bunch of models that are consistent with your data, and then I've plotted those each as a color in this plot. And basically, the value of this plot is that if all of your points are in a cloud in one place, that means that the acceleration is constrained, whereas if they come down here towards zero acceleration, then they're not constrained. And so it's as simple as that. And so all these ones up here, these are the ones that I'm interested in, because there you have an acceleration. And because of the way this thing is just a cutoff because of the way that I did the modelling. It's impossible to have a point come down here because of the way that I did the models. And so now what I could do is I could compare these results with what had been inferred before using the model dependent distances to the star. So these boxes here are where these absorption features had been seen in the past, including the distance to the star, which is inferred from the model. And so now I can also put on all of my points into this plot and see if I agree with what had come before. And largely I do. You see objects that are very close to the star with a very high radial velocity. So sorry, this plot is now just the radial velocity, so this is just where the absorption feature is in your spectrum against the distance to the star. And so largely these are just two different subsets of the results. And largely the same thing. But this comes back to your point, is that so I don't have any of these things down here, but that's because it's hard to see the acceleration, because then that's very close to the circumstellar line, and so you can't, that there essentially gets in the way and wipes out. So the fact that I don't see any down here is not a problem. It's just a bias. And so then the one last thing that I can do with this. So remember I said that the model tells you that the closer the comet is to the star, the smaller the coma. So the more the radiation from the star is pushing all of this calcium away. And so you would and so that was the prediction of the model. But now I can do that directly from the data. And so this axis here is the depth of the absorption. So it's telling you something about the size of the thing in front of the star. And then this is the distance to the star. And so when you're closer to the star here, the absorption is lower, and as you get further away, the absorption goes up. So that seems to confirm the modelling. Okay, so that's all I'm going to say about the spectroscopic transit. So all of that stuff was for beta Pic. Now, following on from the discovery of these spectroscopic transits for beta Pic, Alain did some modelling. And I think this was in the build-up to Corot, was it? Yeah, so the Corot mission, which was going to look for transiting planets, was coming. And so Alain asked the question, well, should we see this in photometry? If you have a mission in space which is looking for planets, it's very precise, and so maybe you could see very small dips in your light curves. And so this is a couple of different models, and so this is the decrement in flux, and so this is 0.1% down here, and a similar level on this side here, maybe a bit deeper. But the reason they look different is because the comets have different orbits, and one of them it's going across, almost like on a circular orbit in front of the star. So the star is over here, and this thing goes like this, and it has this tail. And the reason that comets have tails, so you have the small dust coming off, and then the photons from the star push the dust away, and because it's a 1/r squared force, just the same as gravity. So effectively, these dust grains are just seeing a lower mass star. So that's why you get comet tails in general. That's why you get a comet tail here, because these are small dust grains. And so you get this shape where the head of the comet comes in and the light goes down over time, but then because of all of this stuff here, then it comes up more slowly. And so this is a characteristic shape that you would expect for a comet transit. But if your comet that's if it's going across like this, but if it's coming towards the star, then the tail is not so spread out as the comet goes across, and you get a more symmetric transit. So this was 1999, and there were no papers on comet transit from Corot, not that I remember, and so there was nothing for a very long time. And the first thing that may have been a hint of comets around other stars is this. You may have heard of this star in the news, Voyager's star. It's also known as KIC 8462852, which is not very memorable. But this was a star that was observed with the Kepler mission. And it's just a normal F-type star as far as we can tell. But during the Kepler mission, it had these very large dips. So this here is, 20%. These different lines are just slightly different scenarios. All of the light curves are basically the same, just whether they're shifted up or down or not. And so here you have this 80% dip about 800 days into the mission. And a few years later, you have this series of dips, and there's a zoom in of one of those here. And so these are they're sort of on day to week timescales. And so one of the things that we did, so this is an image from a paper by Mark Wyatt and a few others, and basically we were suggesting that you could get something that looks like this if you have a string of comets in a single orbit around the star, And the reason that you might expect that is if you have a comet and it comes close to the star, then it breaks up and it will spread around into a ring that looks something like this around the star. So if you have all of these objects spread out in a line, but not neatly, they're sort of clumped up, then maybe you could get a light curve like this. But this is not a unique scenario. This is not a smoking gun. These are definitely exocomets. So what we had to wait a few more years, and so then this was the first detection, again using Kepler data, of something that looks very much like the predictions. And so this is nearly 20 years. It's a long time to wait. And so this paper, so Saul Rappaport wrote this paper where they discovered 2 stars that showed these comet-like events. And I've even the scale, so this is 0.1% here. So even the level of the absorption seen by Kepler is very similar. And so that was quite, I think it was quite compelling evidence that you see something that looks exactly like was predicted. It doesn't mean it's definitely comets, but it might tell you that the models are on the right track. Now, the thing here is, so Kepler looked at several 100,000 stars, and these guys are just going through the light curves by eye, which is crazy, but it's kind of cool also because the guys who are doing this are amateurs, so that they go to work and then they come home and then they look through Kepler light curves, which is, well, it's really great. But I thought that was really crazy. I was like, why don't you, because we know if they really look like this and we have a model like this, you know what you're looking for. It should be really easy. And so, and on the day that this paper came out, I went over and I said to some of my colleagues, I said, we should do this. It'd be really easy. And even though this is my paper, most of the work was done by a 4th-year student in Cambridge. He was a very good student, but it was still, in a short period of time. And so what we did, so this is just an example. So this is a light curve for a few months, which shows some variation. So this one here, it's periodic, and this is probably a spot on the star, and the star is rotating, so you get this modulation. And so we did a few things to try and make the light curves a bit neater, so basically a bit less noisy. And then we make a plot where you basically take a running average over the light curve, and then you make this plot, and then you change the width, and then you do the same thing. And so this here is the width of that average as a function of time over the light curve. And then this is the color is basically a measure of the signal to noise of any dips. And so this here, this is really obvious, but this here finds a dip, and the signal to noise is maximized somewhere down here, so for a width of about 1 day. And again, you can see from this plot the precision is about right? So we're looking for things that are about 0.1%, and the variation in the light curve is less than 0.1%, so it should work. And the answer is that it did work. So we basically ran this search for all of the objects in the Kepler field, and you look for all of these individual transits, so you can make a plot which is the signal to noise and some kind of asymmetry parameter. So we're looking for these light curves that come down and then go up slowly as if there was a comet going in front. And so basically this axis here is how much better is an asymmetric fit than a symmetric fit. So we fit a Gaussian, which is this curve here, and then we fit a Gaussian with an exponential, which is that one there. And then this axis is how much better is the asymmetric one than the symmetric one. And then we put all of these dots on this plot, and because we didn't want to look through all of the light curves by eye, there are about 7,000 dots on this plot. And then we drew a box that we knew contained the previously discovered ones, and then we looked at all of these to see if there are any new ones. And some of these just turn out to be discontinuities in the light curve. There's a jump, and then the fitting goes wrong, and you get something in this box. But there was one star that did show some new dips, and we also recovered the old ones. So the method was good. And then, so this is just showing what those three stars look like. Now you can already see that we're not so far off the noise level. So this is getting close to how good it is possible to do. But so one of the things that worries me about this is that, so you see these dips, but that's all you have. There's no, this is just monochromatic in one filter. There's no colours to tell you whether it's red absorption or blue absorption. And so you don't necessarily know what this is. But one of the things that you can do is make just an HR diagram. So this is using Gaia, because of course I'm sure you know Gaia is amazing, at least if you work on things nearby. So what this shows is all of the stars that are near to these ones on the sky. So in that part of the Kepler field that Kepler observed. And then I could put these ones that we found comets around on that plot. And so you're not just selecting stars randomly. They are early type stars, and because they're down here, not up there, that also means that they're reasonably young. And this is probably a good thing. We think in the solar system that all of the dynamical activity happened early in the solar system, and so the fact that these are young is probably a good thing. And it doesn't confirm that these are large comets going in front of these stars, but it tells you maybe we're on the right track. Why they are A and F type stars? Maybe there are just more comets around these stars. So now this is kind of cool, because now we have the TESS mission, which is looking for yet more transiting planets, but this time around bright stars. And so what this is a light curve of Beta Pictoris, so the one that I was talking about before in spectra, over several months, about 100 days, so 3 months. And basically it looks mostly like noise. But it's actually quite good in terms of its precision. So this is the good thing about TESS. It can look at a very, very bright star. So this is a naked eye star, but because of the detector, you don't lose flux. And so even though it's very bright and the electrons are falling into nearby pixels, you can still make a good light curve. And what you can see here, maybe if you squint, is there's a little dip here. But we can do better, because it turns out that most of the noise in that plot is not noise. If you zoom in, this is just one day. Beta Pictoris is a pulsating star, so the flux is going up and down on quite short time scales. And so what we did is, and I should say again, this is work done by a master's student in Austria. So you can fit all of those variations and then subtract them, and now your light curve looks something like this. And the units on this are basically in units of 0.1%. So the precision is good enough that you should be able to see these same dips that we're seeing with Kepler. And the answer is yes. So if you subtract those pulsations, then you get a very precise light curve, and you see 1, 2, 3 dips. And again, this is no guarantee that this is an exocomet, but it has the shape from Alain's models, so it gives you a clue that maybe it is what we were looking for. Now, I think there are possibly some problems with this, or at least our interpretation is a bit too simple. So what you can do is you can make a model of this object going in front of the star. Now, you can't actually measure the velocity, because you could have it be going very fast with a hard front edge, slow with a hard front edge, or you can make it more diffuse and have it go by very fast. But if you assume that it has a hard front edge, this comet coma, then the velocity is actually very slow. But if this is the same kind of object that we were seeing in the spectra, those things are a few tens of stellar radii, so they're really close. So they should be going really fast. So the way that you might be able to do that is if you have a very radial orbit. But then if you go back to Alain's models, if you have a very radial orbit, you expect a symmetric transit, which is not what we see. So this is as much as we did in this paper. There's more thinking that needs to be done for this. Okay, so I think what I'll do is I will just say one thing before I wrap up, is that there is a third way that we've been looking at potentially cometary evidence for comets around other stars, and this is with this large binocular telescope interferometer. So I won't go into how it works, but basically it's a mid-infrared instrument that is very sensitive to dust near to nearby stars. And what we have is we have some detections where the dust level is too bright to explain by something like an asteroid belt. And so the possible explanation is that you have comets that are coming in, sublimating, leaving a lot of dust. This is an ALMA image of one of these objects where you have, so this is a debris disk at 150 AU, and then we have a detection of dust at a few AU. And so this is an independent line of evidence that we think is telling us that there are comets near to other stars. All right, so just to wrap up, so basically I've given you a few different ways that it looks like there are comets near to other stars. I think there's a lot of work to do because you can see the evidence is not obviously comets, but it seems to be consistent with comets. There's a lot more work to do. I think the most obvious thing, so TESS mission has just been extended, so we need to make sure that we're taking spectra when TESS is looking, because it should get more of these dips, and so if we can have spectra at the same time, then we should be able to learn something. And then, I have a summer student who's going to look more in the TESS data starting in a few days. But hopefully we can make enough progress that we can actually start asking questions about how do these objects form around other stars, what kind of regions do they come from. Thank you.
Thank you very much for this nice talk. So, questions? Yes.
Yeah, thank you, Grant. Very nice talk. So I was wondering, can we put any sort of constraints on the size of these bodies that are transiting the stars?
So you can constrain the size of the coma. So it's hard to constrain. So if you go back to Flavian's paper, this plot here, and you get this from the spectra so you can figure out the fraction of the star that's covered by the calcium absorption. That doesn't tell you how big the comet is because the comet is 10 kilometers across or something. So, and if you had a 10-kilometer object go in front of the star, we wouldn't see it. So it depends. So you can I think you can constrain this in a model-dependent way, in that if you build a model like these guys have done, where you have some flux coming in and then some ice sublimation, but it's not well constrained. I would say you can say something about the size of the coma.
Mm. Yeah, no, that's what I meant.
Yeah.
You know the size of the coma, so then you can use maybe another model that would tell you the size of the body. That would be difficult, but maybe.
Yeah, and then you have degeneracies. How efficient is the sublimation?
Mm. Yeah.
Thank
We
you.
would like to know the answer, but it's hard, of course.
Just out of curiosity, are people using your acceleration estimates to constrain the mass of the central star, or it's not helping, it's already well known, or?
It's, we don't have enough, so that's built into the model, so that I measure the orbit by assuming the mass of the star. So the mass of the star is basically estimated from stellar models. Maybe astrometry. Yeah, actually, so yeah, now Gaia has done this, because we know the orbit of the planet, and Gaia has measured the movement, and Hipparchus measured the movement of the star. So that's where there is a constraint, but not from me.
Okay. And if I can ask a very quick question, you showed these rings from ALMA. Do people understand why they're so narrow and regular, or?
Not really. They are more often narrow than they are wide. Sometimes they are wide as well, but we think that they're regular just because there is, in most cases, nothing perturbing them. It's not quite, so what...
Some of them are clumpy, right? So
yeah, although there's not strong, if we look at, so most of the clumps that you see in this image are noise. So something like this is this top one. This is consistent with being smooth, and it's just, so I didn't say this. These discs are quite, ALMA is amazing, but these discs are quite faint. And but one thing that you may be able to see, this one here is actually offset from the star. The center of the ellipse is not in the same place as the star, so the ring is eccentric, and we think that a planet is pushing. But no, so this one here is wide and it has a gap in the middle, whereas these other ones are narrow. We can say planets, but we don't know. We would like to know, of course.
Thanks a lot for your talk. It was great. I have a question about that, actually. Do you have detections of other species, like H2O or CN or any other molecules that you expect to find in comets?
Not yet. So CN is one of the obvious and also one that we expect to be the brightest. I almost put a plot in where Lecavellier has made a plot which is basically shows them in order of expected brightness. And one of the problems you have for something like water is it gets photo, or they all get photo dissociated. So CO is we have carbon, but carbon is in CO, and we have oxygen. Maybe CN maybe we'll do, but I guess there's two things. The chemistry is not as rich, and you look in a protoplanetary disk and people are seeing large-ish molecules. I guess what we're imagining here is you have this icy body and it breaks up, and CO, CN, a few other things come out, but then they just get photo dissociated. And so this is something that Quentin works on. So we have all of the CO, and it gets broken up almost instantly. But then so there should be lots and lots of carbon and oxygen just sitting there, and we're trying to detect it.
We see that in the interior of the
Yeah, and so then you also see it in absorption as well. Yeah, exactly.
I have another question, by the way. Do you plan to use your automatic search on tests?
Yep, starting.
Yeah.
So today's Friday. On Monday, student starts, and we'll just use the same software. Hopefully it's easy. And I think it's very good because the beta pic, right? It has all of these oscillations, and our method does a Fourier transform, takes a peak, removes it, and it takes out sinusoidal signals. So it should be very good for if we don't find beta pic, we're doing something very wrong. So hopefully it works. It's very encouraging that beta pic shows this.
So what do you expect from more observation from beta peak, because that has been already a lot of
So TESS will observe it. So I think something that would be very good to do, so we have these spectroscopic absorption features, and we have now some photometry, but we don't have both of one absorption event. So when the TESS mission has been extended, it will look at beta pic, I think in 2021. So we need to make sure that the HARP spectrograph, or every spectrograph that we have, is observing it for that window, because then maybe this problem that the model for the photometry and the velocity don't appear to agree, maybe that will help. there's always more things you can do with beta pic because the signal to noise is high. But I think that like the next thing that we need to do, that would be on my list.
So thanks the speaker again. Thank you very much.